In this video, we will look at some combinatorics problems that will help you get started on the topic. These are very simple problems, nothing too fancy. Let's start with the version 1 of the problem, where you are given n boxes, and in each box you can place any integer from 1 to m, and you have to find out the number of ways to create unique arrays after doing the placement of n integers. So how do you solve this problem? You can see that whatever number you place in this box, this will be independent of whatever number you place in this box. And how many choices do we have? For the first box, you can place any number from 1 to m. So there are no restrictions. So there are m choices for the first box, m choices for the second box, m choices for the third box, and so on. And since all the choices are independent, meaning if you place a 3 over here, no one is preventing you from placing a 5 over here. So that is why, since all the choices are independent, the total number of way comes out to be m to the power n, because you will multiply m n times. N is the length of the array. So this is the number of unique arrays that you can get where each element is between 1 to n. So far so good. This was the simplest version of the problem. Now let's make it a bit more complicated and we'll go on to version 2. And in this version, let's add an artificial condition. Like initially the array was empty, but this time let's add a binary string. Like let's create a bitmask. So we add 0, 1, 1. Some places we add 0 and some places we add 1. And the problem setting is still the same. This array is of length n, and you are allowed to add integers from 1 to m. However, there is an extra constraint that you are given an integer x, okay, and at all the locations that 1 is present in this bitmask, at all the locations that 1 is present, the number that you place should be greater than or equal to x. So at all these positions, the number that you place should be greater than or equal to x, and all the positions that contain a 0 at their bit value, you have to place a number that is strictly less than x, but those numbers should still satisfy the original constraint, which is that all the numbers should be in the range 1 to m. How do we solve this version of the problem? So you can see that still all the choices are independent. Whatever you place over here will not affect this. So let's solve each box independently. So if it is a 0 over here, it means that you can place only numbers that are strictly less than x. So it means you can place 1 till x, right? And since it is strictly less, so how many choices? You can include 1, but you have to exclude x. So there are x minus 1 choices. What about the place where you have a 1? Then you have to place numbers that are strictly greater than x. So how many choices will there be? So that would be, you can place any number between x to m. And how many entries are there total? So that is m minus x plus 1. So what is the final answer? So the final answer is, you multiply x minus 1 every time you see a 0, and you multiply m minus x plus 1 every time you see a 1, and you repeat this n times, and the final multiplication of whatever terms that you come up with, that will be your answer. So in this way you can solve the version 2 of the problem. Now let's move on to the version 3 of this problem, where you are given, so this array is of length n. And in the previous version, you were given a fixed bit mask and a fixed x, and you had to compute the answer for this. So you iterated it over all the bits in the array and then decided on the possible choices that you could make. But now let's make this problem a bit harder by having the array of length n. But now you can notice that there will be 2 to the power n possible bit masks that you can create of zeros and ones. So let's create all the bit masks. So for example, if n is equal to 3, what are the possible bit masks? So it could be 0 0 0 0 0 1 0 1 0 0 1 second. So it will be 0 0 0 0 0 1 0 1 0 and 0 1 1, and then finally it will be 1 0 0 1 1 0 1 0 1. So how many there are? It should be a total of 8, right? And how many have we created? It is 4. So we are missing 1 over here. So which will be 1 1 1. So you can see that there are these total of 8 bit masks. Okay. Now the problem says that for each bit mask, so each bit mask has a number associated with it. Each bit mask has true or false written with it. So suppose this is true and this is false, this is true, this is false, and so on. And your goal is to find out for each x. So define f of x comma bit mask as the number of ways to add numbers from 1 to m such that the ones in the bit mask indicate that you have to place a number that is greater than or equal to x, and the zeros in the bit mask denote that you have to place a number that is less than x. So this f of x comma bit mask is nothing but the answer for a fixed position that we solved earlier. So your goal is to find out the sum of x over all x from 1 to m and all bit masks which are in the true set. So there are some bit masks that have a label corresponding to it as true and some that have a label corresponding to it as false. So you only need to look at the bit mask that have a true associated with it. So how do you solve this version of this problem? So the naive algorithm that you can come up with is something like this. You can iterate x from 1 to m, and then you can iterate bit mask from 0 to 2 to the power n, and then you can compute the answer in O of n, because you are iterating the all of the bits to compute this product. So you iterate, so it will be O of n. So the overall time complexity becomes n into m into how many bit masks there are? 2 to the power n. So this is the overall time complexity. Ignoring the time complexity for computing the powers, but anyway, that will not be a problem. So can you improve it any further? Like, can you remove some factors from here and there and maybe reduce the complexity down? So to do that, let's notice that in the fixed bit mask case, did we really need to iterate through all the bits of the bit mask? So if you had 0 1 1 0, And if you this bit mask is fixed and you are given a number x, so did you really have to travel through all of these elements and then apply the choices? You can see that the ordering does not matter. Only thing that mattered to you is whether that element is 0 or whether that element is 1. So the only thing that mattered is the count. So suppose in this bit mask, the answer is Z. And if I reshuffle this bit mask and create a bit mask like so, 1010. So you will see that these two bit masks, the answer will be the same for these two bit masks, because you will apply the same choices whenever you see a 1 or when you see a 0. This means that we are only interested in the count of ones in the bit mask. So let's say you maintain for any bit mask, you maintain the count of ones, count set bit. Okay. And let's say this count is CNT of mask. Okay. This count of mask represent how many set bits there are in the mask. Or let's call it as C. Then can you instantly compute the answer if I tell you the count of set bits in the mask? Yes, because if there are C set bits, it means that at C positions, you are allowed to make m minus x plus 1 choices. So the answer would be m minus x plus 1 to the power C. And at the remaining positions, you can only take x minus 1 choices. So the remaining positions would be x minus 1 to the power remaining slots, which is n minus c. So this is the answer for a fixed bit mask. So you can see that previously we solved the case for a fixed bit mask in O of n by traversing the entire bit mask. But this time we are only relying on the count of the set bits in the bit mask to get this expression. Now we know that we can at least get rid of this O of n factor over here. And once we have gotten rid of this O of n factor, then the complexity becomes m into 2 to the power n. But can we reduce it down even further? So you will notice that you are given all the 2 to the power n bit masks and their classes, whether that will land in the true class or in the false class. So if you have n and you will have 2 to the power n bit masks corresponding to it, and you already know all of these bit masks. So you can divide these bit masks into n different classes, which will be disjoint. And those classes are the bit masks with 0 bit set or 1 set bit, 2 set bit, 3 set bit, and so on. And how do you do that? So you are initially given a list of all the bit masks from 0 to 2 to the power n. So you have 0, 1, 2, 3 up to 2 to the power n. So you simply iterate over all of these numbers and then you compute the set bit count of this bit mask. And if this bit mask has a true written besides it, that is if it is allowed to take this bit mask, the true false case, then this means that this is a valid bit mask. And suppose the set bit count is k, then at level k that you are maintaining, you go and increment the count. So you will recall that for each bit mask we only had to maintain the number of set bits in that bit mask. We didn't really have to track the entire bit mask. So two bit masks with the same set of set bits, they are equivalent. So now, given the initial 2 to the power n bit masks, we can now split it into only n bit masks. Not exactly bit mask, but only n different classes, and each class will represent how many bit masks are there with a value true and k set bits. So suppose there are 5 bit masks and then there are 3 bit masks, 2 bit masks and 2 bit masks. Now, once we have this answer, then we can try to solve this problem again, and we can see whether we can try to see if we can reduce some factor from this time complexity. So we have to compute f of x comma bit mask for all the bit masks. So you know that to compute it, you have to iterate x from 1 to m, and then you have to iterate mask, and then you have to iterate all the bits in the bit mask. So we already saved this factor of n, and now we want to see whether we can remove this 2 to the power n factor. So how do you do that? Now you can see that this time you only have to iterate over x for x in 1 to m, and now you don't really have to iterate over all the 2 to the power n bit masks because some of them are identical. So you just have to iterate over the set bit count. So if you define as set bit count, so this set bit count, this can only be in the range 0 to n, right? And how many uh, how many bit masks are there with this set bit count of k and true written with it? So suppose this number you must have already tracked it over here. So suppose that number is 5, or like let's say that number is k. So you have to add, so there are k bit masks with set bit count as sb count, and in these k bit masks, let's define set bit count as SC. Okay, so there are a total of SC bits where you can place a 1. So for you will have m minus x plus 1 to the power set bit count. So SBC into x minus 1. So x minus 1 to the power n minus SB count. So you just have to sum this expression over all x, where this ki represents the set bit, ki represents the number of bit masks with set bit count as SBC. So you can see now that the time complexity is simply O of, so this has O of m and this is O of n. So this is overall time complexity would become O of m into n. So now we are able to reduce the time complexity from n into m into 2 to the power m to simply n into m. So that was it. Like this was just a simple combinatorics problem that I wanted to discuss. In case you are interested, like what is the motivation for this problem and where is this expression of bit mask dealing with combinatorics coming from, let me know in the comment section, and I will link down the problem, the original problem in which this problem appeared as a sub problem. So if you want to solve that, you can do that. And yeah, that's it. Thank you.